What I'm here today to share with you is a little bit about standing wave ratio and seeing standing wave ratio. I would like to thank those who've already seen this presentation at the Ears Club. It's quite flattering that you decided to watch it again, and I'm even wearing the same tie that I did then. And what I'd like to do before I begin is to give a little bit of thanks to Bill Hayes, AE 4QL from Kentucky. He did a presentation for his club out there, and it's called Standing Up for Standing Waves, and it's actually on YouTube. His is an hour-and-a-half presentation that's on episode 199 of Ham Radio Now, and I will not do an hour-and-a-half presentation for you, minus 2. So, actually, mine's about a half an hour, and I'd also like to thank Dave Cole for having shared the video with me a little bit more than a year ago, and having been my consultant during the time that I was trying to build the apparatus myself, because I thought it was just a wonderful way to see standing wave ratio. I'd also like to thank Kelly Wilson, who's here tonight, who helped me with the, which you'll see a little bit later, which is a virtual simulation of a standing wave. And I would particularly like to thank my wife, who's here with me tonight, because not only did she encourage me, but she allowed this apparatus to be up in the family room for a little over a year on and off. So she deserves a lot of credit. The room looks very different when it's not there. So first, I'd like to give you just a representation of what a physical standing wave is. And that's this part of the apparatus. What I have here is an elastic string, and then I have a little Arduino controlled solenoid over here. This will simply vibrate the string that's weighted over here. And what you'll get to see is just a simulation of what happens when you have things vibrating at the right frequency. This is about 5 beats a second, and if you look at it carefully, you'll notice that it's pretty much stationary at both ends, and we've got the amplitude in the middle. This is a half wave, and it gives the impression that it's almost standing still. If we double the speed, it's called a harmonic. If we go to 10 beats per second, you'll notice it kind of goes through this little flutter, but all of a sudden it cleans up, and you have this nice, complete 360-degree wave. It's essentially standing still here. You see the amplitude here. This is called a node, and then it goes on the other side. So this is 0 degrees, 180 degrees, and 360 there. If we go another 5 beats per minute, after a little bit of flutter, you get this nice wave and a half. We've got a node here, here, there, and at the end. And again, we can get an additional harmonic. There you have 2 full waves, 0, 180, 360, and then at the end. And it can actually go 2.5 waves. And this is really about at 3 full wavelengths. But what you really want to notice is that instead of a traveling wave, what you end up with is actually amplitude here, a node there, amplitude, and another node. So that's a physical demonstration of what a standing wave is. Now to get into the electronic version. The apparatus that I have here, what I want to show you is what it's built, how it's made. First, we have over here a high-quality precision instrument, both UV5R, and it's transmitting at 5 watts at 145.1 megahertz. The antenna system is actually, it would be perfect if I could transmit at 138 megahertz, but since there's so many OOs in the audience, I decided that would be a really bad idea. But what we have here is an extended push-to-talk switch. That's also connected to a little Arduino down here that keys up every 10 minutes to make us legal. And then we have right here, this little box is a standing wave meter, an SWR meter. And then right here, we have a 4-to-1 voltage balance. That's because the radio transmits at 50 ohms, This antenna system is a 200 ohm system, and 50 times 4 gets you 200. So this is a 200 ohm, a 4-to-1 balun. We also have, it connects to these two 10-foot copper poles. They're just pipes that I got at Jerry's. And down at this end, at this point, I have a 200 ohm dummy load. I also have some other dummy loads that are ones that are 400 and another 800 ohm dummy load. Additionally, I have over here some voltage detectors. This is just a light bulb. And I have a current detector, and I'll show you those in just a moment, along with the wave generator. What I intend to cover tonight is a basic overview of standing wave ratio. Not lots of details, not lots of math, on purpose, because I figure if we have a very clear idea of what the basics are, then when we see the math and all the details, it will still make sense. So, because of that, we're also going to assume that all of the concepts that we talked about at the very beginning are happening in free space. There's no interference from anything. Waves propagate perfectly. There's no unusual things. The math works out all perfectly, because that's a whole lot easier to describe than getting into the details right away. So with that, what I'd like to do first is to explain what we're trying to do and then show how this all works. If you were looking at the goal of propagation of a dipole, what you would see from a top view is essentially the electrons sloshing back and forth, much like they would in a water bottle, sloshing back and forth. The individual molecules aren't moving very far, and from what I understand, the individual electrons in a dipole actually only move about 2 millimeters, which isn't respectively very far. But that sloshing back and forth, the motion creates the current, and then when they slosh all the way to one end, you get a voltage difference from one end to the other. So that's a big picture of it, and when they do that, they propagate these wonderful electromagnetic waves that we then use to enjoy our hobby. If you were to look at that same dipole from a side view, what you'll notice is we have the electrons overly represented in moving, but as they slide back and forth, you end up with this shape where the electrons are way over on this side, so you have a really strong negative charge, and not so much on that side. And you'll notice that this is a half wave. That 180-degree half wave is really important to notice, but so is the fact that it's created by these electrons flowing back and forth. And notice that the feed line for this antenna, those electrons are flowing the opposite direction. So in order to end up with this 180-degree out of phase at the very end, you have to have the feed line with the current going the opposite directions as well. So with that, you need to understand what waves do when they interact. As they go up and down the feed line, there's really, fortunately, only two things to remember. They either are constructive or destructive. In this case, you have constructive waves. As they run into each other, you'll notice originally on the right side, you have the little wave, and then as it interferes with the other one, you get a sum of the two, and then the little wave continues off to the left. That's a constructive wave. Sometimes you can have negative voltages or negative waves going the opposite direction. This is the same idea. You'll notice on the top, the wave on the top, but this time when they hit each other, since one's negative and one's positive, we're still adding. But anyway, but the waves essentially disappear in the middle because they are equal but opposite. And then as they continue to go down the line, they reform. So essentially what you want on a nice, perfect system is that you want the waves that are coming down the feed line to interact like this. In this case, you want one wave on the left side to be, say for example, going up and down, and then the other wave on the right side, you want actually the opposite, because right here, this is the sum of the two. If they are 180 degrees perfectly out of phase, then the interference causes no situation, no waves in the middle, okay? That's the goal. Now, with that, let's talk about how this is built. In order to get one wave, for example, out of the transmitter through the SWR meter here, part of the thing the balun does is the current goes to this back pole here, through the back pole, and say, for example, when it hits this line, it would go up and then down and up and down. This delay line causes it, if this were not connected, if the delay line wasn't here and it went here, you'd have both of them going up and down, and then their interaction would be twice as high. And so what they do is, we have it, for example, going up while it's going through this little cable, so when it reaches this point, this is going down while this one is going up. And so you have this kind of interaction. So while one is up, one is down, and then you have no interaction in the middle. So, this is why, when you get your technician's license, they want you to actually calculate the distance and frequencies, because in order to build this little delay line, you have to know that we're dealing with 145 megahertz. Lambda, the little upside down V, is the wavelength. C is the speed of light. With a little simple algebra, you recognize that the speed of light divided by the frequency, in this case we're using metric, the speed of light divided by the frequency gets you a 2 meter wave, full 360-degree wave. And ta-da, that's why when we talk about communicating on 145 megahertz, we're talking about 2 meter rigs. But we want this actually to be only 180 degrees out of phase. So we need to cut this in half. And so now you have a half a wave. Problem is, that's in free space. And since there is really no free space, as soon as waves start traveling through something, they don't always travel at the speed of light. And so what we have to do is recognize that we may need to make some compensations. You can look up on a table for any coax manufacturer what their velocity factor is, but essentially what they're doing is they're saying, you know, through this particular material it's going to travel at 82% the speed of light. So we multiply that by 0.82, and then we also have to do some actual measurements because we do have couplings and that kind of thing. So roughly, this little segment here is the distance that a wave at 145 megahertz is traveling to go half a wavelength. So that when it hits here, it's now half of 180 degrees out of phase. So with that, now let's look at what electronically we would start to see when we do our wave. This is an animated wave manipulator, and what you will see here is this. This is a traveling wave. And this is the same thing that you saw in the still. We have the left side, the right side, and you'll notice that they are 180 degrees out of phase, and then the sum of the two is that green little line there. That's when everything's perfect. Problem is, that doesn't always happen. Yeah. Well, when it's traveling, depending on what metal it's traveling through, the velocity factor is affected by a number, but essentially what it's traveling through. But also the metal as well. So, if we were to have this not quite in phase, 180 degrees out of phase, say for example it's 190 degrees out of phase. What you'll notice is the green, you start to see this green traveling wave. If it continues to get out of being perfect, you get something that looks more like this. But once it is not completely balanced, it doesn't terminate at the end of our dipole the way it's supposed to. And so it actually causes a reflection. And so what we'll do is we'll add a reflection here, and I want you to watch what happens to the sun on the bottom. It now becomes, instead of a traveling wave, it gives the appearance that it's a standing wave. And you'll notice that the red, by the way, is the reflection. It's going the opposite direction. And you now have a standing wave. You'll also notice, though, that in between there's sometimes a little bit messy. It's not always perfect. And if you change the amplitude
you can also change what happens. For example, if your feed line isn't, well, if your feed line is really good, you can have really high amplitude. The irony is, if your feed line is really bad, it doesn't mean things are good, but it does, for example, lower the height or the magnitude, the amplitude of your standing wave. So, anyway, that's what the simulation looks like. The other thing to consider, though, is if it's reflecting once, then it also, when it comes back this direction, it's going to hit this. It's still, since it's not terminated correctly, it's going to reflect back, and so you have smaller reflections back and forth, and then it eventually gets very messy. Eventually, those waves, they never disappear. It's one of those wonderful laws of physics that no energy is ever lost. Eventually, some of it will transmit. Some of those waves will actually transmit, but a lot of it will also turn into heat. And that's not always a good thing either. So, how was standing wave ratio originally discovered? Well, it turns out that before World War II, most antennas were fed by twin lead or ladder line similar to this. And some enterprising ham thought, you know, if I've got current going down this line and that line, what would happen if I took a light bulb and I put it between the line? What would happen? Well, lo and behold, it lit. Biggest thrill of any ham is when the lights go on, and you can see the same thing here. If we turn this on, make sure it's transition. You can't see it very well, but there is a tiny bit of current here just to turn this slightly orange. There's a little bit of current between this line. Now, if I were running, this is 5 watts. If I were running this HF rig, this would be substantially greater. But what they noticed was that if they ran this light bulb up and down this twin lead, when there wasn't any change in the brightness of the bulb between the high and the low, their propagation seemed to be good. They got good signal reports. What they noticed was, as well, that if the propagation, the signal reports were really bad and they went and tested it, what they discovered was that there were large differences between the voltages at different points of the feed line. So what we're going to do is we're going to take an 800 ohm terminator. We're going to change our standing wave ratio from roughly 1 to 1, because it's a 200 ohm system. We're now going to change it to a 4 to 1. And what I want you to notice is, when we key it up, we have, can you see the light? Just a tiny bit of a light there. No, actually, I'll show you this in a moment. But we've got brightness here, and if we slide it here, there's nothing. That difference between the bright and the dim is standing wave ratio. That's how the whole thing came about. And so what we've got is, as you slide the light bulb up and down between the feed line, the difference between the maximum voltage and the minimum voltage was what you got to a standing wave ratio. What they called then a voltage standing wave ratio. And what came out later was, as most of us know, after World War II, there was a surplus of coax. People decided to use that as feed line, and they also realized that it's not very functional to try to run a light bulb up and down your feed line using ladder line. And so they needed to come up with a different way to measure standing wave ratio. So they came up with this setup. Over on the left is the transmitter, a little blue box, like we have right here is their SWR meter. And what they're measuring now is forward voltage plus any reflected voltage divided by the difference between the forward voltage and the reflected voltage. And that's now what we call standing wave ratio. Not quite the same, but it functions very, very similarly. Problem is, with this little apparatus, that this light bulb is a short. If I put this here and I'm measuring the voltage here, it changes the SWR down here, it changes the standing wave ratio over here, and by the way, it's keying up to ID itself. But anyway, what you notice is that we've got a short in our detector. That's not necessarily a good thing. So what we want is something that detects, instead of voltage, I wanted something that would detect without interfering. The problem is that if you decide to power something instead, so if I wanted to have something with real high resistance so I could measure the voltage without interfering with the standing wave ratio, that everything seems to affect antennas. Little batteries that are metal that I would have in my little equipment to provide some voltage to test, to turn on the lights, since I didn't want to have using the actual current from the rails to run it, caused problems. So batteries also coupled with the antenna. Water does. For example, if you take this is a current, let's see, let me turn this on right there. If you put water in a certain spot, it changes the antenna. We all know, those of us who've ever messed with rabbit ears, that you change standing wave ratio. Okay? Okay, hold your foot up. Remember, okay, stay right there. We all remember those days. But that's because we then couple with the antenna propagation and create change. The distance it is from the ground changes things. Plus, the test equipment itself changed things. What made it harder was I discovered that the RFI produced from the apparatus affected my test gear as well. And I started to have RFI ingress into my multimeter. So what you see here is my attempt to stop all of that. I discovered that my wife's stew pot sieve right around here made a great Faraday cage to provide so that RFI didn't go in there, but I also needed to make sure that the wires connecting it to the multimeter were shielded as well. So you see there's a ferrite choke right there. There's another ferrite choke right here to stop any RFI from coming down the line. The problem is that that didn't always work either. So it turns out that a certain measurement of capacitor functions like a short for RFI. So we have a 0.01, I forget what, 0.01 microfarad capacitor there to provide a short so that the meter actually read what voltage was really being done on the rails. But anyway, suffice it to say that everything seems to affect antennas and they can affect other things. But when I finally isolated it and I measured the voltage, this is the actual voltage graph that I got from this very system. And what you'll notice is the forward voltage was pretty steady. The forward voltage down here, the reverse voltage was also very steady. And there was a slight difference between the two, which is why when we turn this on, we get a little bit of light right here. However, again, this is a short, so what I did is this is a current detector. There's a little wire underneath the circuit board that picks up the flow, which is just the opposite of the voltage. And so, for example, right here, we have high voltage and low voltage. Where the high voltage is, it's very dim with the current detector, and where there's low voltage, there's high current. So when we make the switch, just remember that we're just looking at the same situation, but opposite in terms of detection. So now we will put 200 ohm terminator back on here, and I'll show you how this looks in the ideal situation and in the non-ideal situation. So this is now terminated properly. We have a 200 ohm system terminated by a 200 ohm dummy load. And what you'll notice is if we key it up, we have very consistent brightness over the entire transmission line. If we take another detector, you see the same thing, and notice this doesn't short that. And I have it for you. Oh, there it is. So we've got this nice balanced line. So theoretically, when we attach an antenna to it, we should have good propagation. What happens when it's not balanced? Well, this is the same kind of measurement. So what we're going to do is we're going to pop this off. Instead of the 800, we're just going to use a 400 ohm terminator. This doubles the standing wave ratio. And if you were to look at the meter, it's normally a 1.4 to 1, and then now it's like a 2.8 close, so that's about double. But what we have now is if we key it up, we'll notice that it is no longer smooth across the entire line, feed line. Right there, there's a null. And right about there's a null. Here, we have a bright spot. And here, we have a bright spot. So remember the wave analogy that we did here, the physical wave. What you're looking at is, we've got amplitude here, here's a null, here's an amplitude here, here's another null, and then here's an amplitude here. And what you are seeing is a standing wave. The neat part of this is, here's our little meter stick between the two blue. This is about a little under a meter. Remember we talked about velocity factor. It would be nice that it's a meter, but since it's running through copper tubing, it is about 82%, well, close. Yeah, it's somewhere in the 80s. And it's really hard to actually get these perfectly, but this is a meter apart, that's about a meter apart. And what you're seeing is, say for example, this part right here is our null, right here. This distance right here would be here. Then we've got another null right there. And then here you've got another bright spot there. And so what you're seeing is the standing wave ratio. Because of the interaction between the two lines, it's not completely perfectly balanced any longer. We would take this off and actually put recognize this. This is our dipole, and this is the. I forget the Z at the end of my call sign. I forget this is a hairpin match. Anyway, well, this is functions like a short, but since there's also capacitance in it, this turns out that. Whoops. What you'll notice is this is about a meter, slightly less than a meter. And if we put it on the end here, this system is now balanced. And I want you to remember this was a null and that was a null. But when we key it up, now it's balanced again. So the brightness should be, that should not be happening. Something's loose. I'm thinking, there we go. Okay. Got the detector on backwards, that's why. We're measuring the back right instead of the front. Okay, anyway. Watch this one. But what you'll notice is we've got a nice, again, balanced system. And once we do that, now we can look at our propagation. So let's go out here. This is my favorite little homespun 2-meter Yagi. And what I've done at the end of this is instead of putting a radio, I have this little wire here, and you can see that there's a little LED current detector, so that instead of inductively picking up radio waves and putting them into a receiver, we're just sending it to the LED. And so now when we key this up, this should transmit, and you see that the light lights out. And Rose, I'm going to ask you if you would please be my button pusher for just a moment. Go to the other end. And
George Jetson job.
so what I want you to notice is that at this point, we're now getting some wave propagation. And it will propagate like we've seen in these pictures before. So Rose, get up, please. And what you should notice is we have this nice propagation straight forward. We'll key it up again. We have nice propagation. We'll move this so that we can see it there. Straight up and down. Underneath. From behind. But notice what happens when we're off end here. That it's not very good right off the end. And it's because of the propagation of the dipole you see there. If we're on that little black arrow, off the corner here, this is the whole of the donut. And so the propagation isn't very good. The other neat thing that you can see with this, okay, one more time, Rose, please, is something called polarization, thank you. And that's when the antennas aren't line, you've got horizontal polarization, vertical, and so if we tilt this way, you'll notice that we don't have good reception in this direction. And so polarization is particularly important if you're doing work with satellites and things. But you can see that here is that if the polarization is off, you don't get the propagation that you're hoping for, or the reception. With that, now that you've got a chance to see what the standing wave ratio is, a couple of caveats. First, it isn't always as big a deal. I mean, some people are shooting for that elusive 1-to-1 standing wave ratio. Sometimes that's not feasible. As I mentioned, trying to build this, I figured out exactly where the 1-to-1 ratio was, and it was outside the ham band. I tried all sorts of ways to get it to work, but then all of a sudden the equipment became more expensive and realized 1.4 or 1.6 to 1 was pretty good. And it isn't really always a big deal when you're transmitting, unless it keys in something that happens, particularly with the newer rigs. A lot of the HF rigs have circuitry built in to prevent those voltage spikes that you were seeing. You've got a peak here and a null there. They don't want those voltage spikes to be reflected back into the radio. So what they do is they have these protection circuits that are triggered as soon as it sees a high SWR. It says, I'm not transmitting 100 watts with that. So it lowers the output of the radio. It's not a problem because of your antenna. It's the problem of the radio itself not transmitting at full power. And it's not the SWR that's causing the problems, it's the radio. And so what they do is they will often put in between the antenna and the radio a tuner, which makes the radio think that the SWR is really good. It'll transmit at full power, and then when it hits the antenna system, you can still have a not perfect standing wave ratio, and things will be, for the most part, fine. The other thing is that you need to remember that low SWR doesn't necessarily mean you've got great propagation or great reception out there. For example, we remember when we had a 200 ohm dummy load, we had a wonderful SWR, but there was no antenna, and so it wasn't transmitting at all. You also have a situation where over time, coaxial cable deteriorates, and if it deteriorates, then those reflections become less and less, then your SWR drops, and so you can actually have an antenna system where your SWR looks better and better every single year, but it's because your cable is falling apart, not because you've improved the situation. Another interesting thing is that somebody once said that they actually were able to see SWR sort of like this because they saw in somebody's antenna system, and those of you who went through this recently will appreciate it, there was an ice storm, and there was ice on the antenna, and you could see where the icicles were long and then short, and then long and then short. So that was kind of neat. The other thing to pay attention to about the standing wave ratio is shown in this graph, and that is that even if it's there, it doesn't necessarily change or decrease the quality of your transmission. For example, the way you read this is you look at the loss that's built into your cable, your feed line, and then say, for example, that you have a 1 dB loss in your feed line. 3 dB, by the way, is you've lost 50% of your power. So 1 dB is not anywhere near that. But a 1 dB loss, and then what you do is you look up here and say, okay, if my SWR is 3, right here, that's about a 0.45 extra dB loss because of bad SWR. Compared to the 1.0 loss in just your feed line, 0.45 is not, for most circumstances, always a big deal. Even if the SWR was 4, that would essentially double, almost double your loss, but that's still a 2 dB loss, not a 3 dB loss. And again, that's mostly because of your cable loss in the feed line. So this is something to think about when you're trying for that elusive, 1-to-1 SWR. With that, any questions? I have here a handout that has the link to the Ham Radio Now website and some other websites that I found interesting. If you are interested, I'd be happy to let you look at it. Anybody want to? Here. I would encourage you to come up. I'll let you key the radio up, and you can slide the things back and forth and look at the SWR. And with that, thank you very much.